We're going to be solving different questions on the different subheadings of this topic, UV spectroscopy. All right, now let's look at the question. By the way, if you have not subscribed to this channel, I want you to hit the subscription button. It doesn't bite. We're going to be uploading a lot of important videos on UV spectroscopy. We're going to be uploading videos on high-house spectroscopy. We're going to be uploading videos on NMR spectroscopy. So I want you to stay tuned. I want you to subscribe, and you're going to gain a lot in this channel. All right. So the question number 1 says that name the various transition that is possible in the following compounds, and which of them is UV active. Now, nevertheless, by the way, you need to know that the valence electron may reside in the pi bond or the sigma bond, or may also be in the form of the lone pairs of electrons. And of course, you know, some elements that normally have lone pairs of electrons in equivalent bond. All right, so therefore you could have transition from the pi bonding to the pi at bonding. You may have transition from pi to sigma bond to pi at bonding. You may also have transition from the pi to the sigma at bonding. You may also have from this level of the lone pairs of electron, from the transition from this lone pairs of electron, this is the level for the lone pairs of electron, to the sigma antibonding. You may also have transition from the pi to the pi antibonding, and you may also have transition from the lone pairs of electron to the pi antibonding. So your transition will involve transitions from the lone pairs of electron, from the sigma, and then from the pi to either of this, to the pi antibonding or to the sigma antibonding. So you may have transition from here to here, 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 or transition from here to here. So that is what is happening. So this is the low energy level ones, and then you will have transition to the antibonding orbitals. All right, back to our question. So in this place, we all know that here all we have here is the sigma bond. So there's no other one. So therefore, the only type of transition we can have here is sigma to the sigma antibonding. All right. Now let's look at this place. Okay, so what we have here, of course, here we have lone pairs of electron on this oxygen. We have two lone pairs of electron. Okay, so there's a lone pair of electron here. So of course we also have sigma bond. Okay, so we can have sigma. Excuse me. We can have from sigma to sigma antibonding, or we can have from the N to the sigma antibonding. So those are the type of transitions that we can have. Okay, here we have sigma bonds. So we can have sigma bonds. So we can have sigma to sigma antibonding. We also have pi bond. So we can have sigma to, excuse me. So we can have sigma to pi antibonding, or we can also have from pi to pi antibonding. So those are the types of transitions that can occur. Okay, what about this place here? We have sigma bond, sigma to sigma. So we can also have sigma to pi antibonding. We can also have from pi to pi antibonding. And we can also have from N to pi antibonding, because here we have lone pairs of electron We have lone pairs of electron in this place, okay? So we can also have N to sigma antibonding. All right. So which of them is UV active? Basically, the types of UV transition that is UV active is basically N to pi antibonding, and from pi to pi antibonding. All right. So which is this? And this, then this one in this question. All right. Now let's move to question number 2. And question number 2 is based on the Woodward-Fieser rule for calculating the lambda mass. Okay, so the first question is calculate the lambda mass for the value of the following compounds. Now, when you are talking about the Woodward-Fieser rule, you say that the lambda mass is actually equals to the base peak or the base value plus the summation of the substitute. The substitute on the compound and then plus other contributions. Now, of course, you know that basically in this calculation of the lambda mass, we've of course established that when you have n to pi stars and pi to pi, so pi to pi star, that's when you'll be talking about UV active, the one that, so you're going to be calculating their lambda mass. And of course, this one's occurs in nodes. And of course, this one, more of it in dienes. Okay, so therefore, we're going to be calculating the lambda mass for compounds that have enones and the one that have dienes. Of course, though, of course, we also have this one in single double bond. But for the sake of these calculations, when you will be having a strong lambda mass, you'll be having them in dienes and also in enones. Okay, so therefore, I'm going to be using a short formula that we bring up the whole of this. I will bring the whole of this, and that is for the dienes. So for the enones, I'm going to be talking about it in forms of Fred. And for dienes parent name, we're going to be talking about it just Fred. Okay, now this P is parent value, the parent value. The R is the ring residue. So the E is exocyclic, double bond. I'm still going to talk about each of them. So the D is double bond extension, double bond extension. And the H is homoannular diene component, homoannular diene component. So I'm going to be talking about it later on, okay? So let's look at the first question. It says that, of course, let me talk about the base values, the parent values. Okay, so for acyclic dienes or heteroannular diene, so you are going to have this an acyclic, that means a non-cyclic compound. That's what you call acyclic, compound that is linear, that is not in a cyclic form. So when you have it, That is the base, the parent value is 215. All right, and if it's like this, you can see they are not homohalonide. That is, double bond is not in the same ring, so therefore it is heteroannular diene. And so it is this. So the parent value for homohalonal diene, that is, the double bond is in the same ring, so therefore the parent value is 253. The parent value for an alpha beta unsaturated ring ketones, so it's actually 215. But if it's for 5-member ketones, it is 202 nanometers. So the ring residue is 5 nanometers. A double bond extension, I'm going to explain the double bond extension later. So it's 30 nanometers, and then also the exocyclic double bond is going to having a contributing factor of 5 nanometers. Now, the ring residue for enones are going to be taken in forms of the alpha, beta, gamma, and delta, okay? So the homohalonal diene components had the values of 39, all right? Now, so the first question here, so they calculate the lambda mass of 2,4-dimethyl pentanone, 3 diene, okay? So let's solve the first question. Sorry, we handle this straight. Okay, so question number 1. So let's draw the structure. Okay, so now, of course, you know that this is an acyclic diene, the parent value for acyclic. So, of course, this is a diene. We're going to be using pred here. So, you follow through, you pick them one after the other, okay? So, the parent value here is 215 nanometers. Okay, so now here is here the diene. So we're going to talk about, we want to select the ring residue, of course, in this case, because this is an acyclic, we're going to be talking about them in terms of methyl group, the ring residue. So we're going to be talking about them in terms of methyl group. Now, these are the dienes. The carbon involved in the diene are carbon 1, carbon 2, carbon 3, carbon 4. So these are the ones involved in the dienes. So any methyl group joined to them are the residue. So that's the methyl group that is joined to them, all right? So we have 3 methyl group. So that's 3 ring residue. That's going to be 3 times 5. So that's 15 nanometers. So the next thing we go about is exocyclic. Of course, there's an exocyclic here. So what about the double bond extension? There's no double bond extension. That means after this diene, there's no other double bond after them. So therefore, you add them and you get your answer. So therefore, the lambda max . So it's going to be 230. Okay, so let's look at question number 2. So it is already a rough diagram. Permit me to change my pen since that is giving me some kind of problem. Now, so let's look at question number 2 here. So let's look at the question number 2. So here, you have to find the lambda mass, okay? Now, of course, this is a, when you look at this compound, you will say that this also, the double bond here are not in the same ring. So there's one double bond here, there's one double bond outside the ring, okay? So therefore, let's talk about the parent value because so parent value, which is an heteroannular, so it's going to be a 215 nanometers, okay? The double bond are not in the same ring, okay? Now, okay, so the next thing we're going to be talking about is the ring residue. Ring residue. Now, the ring residue, you first identify the double bond, I mean the dienes. This is one heme, this is another heme. So one, so the carbon bearing them, 2, 3, 4. All right. Now, when you look at this one, there is an extension. This double bond here is also conjugated to this. So you extend, you continue to talk about it. So you also involve the carbons there. All right. Now, what are the subsequent residue joined to these carbons bearing the dienes and also the extension? So you have this one, you also have this one, you also have this one, you also have this. So that means we have 4 ring residue, 4 ring residue. So that's going to be 4 times 5, which is going to be 20 nanometers, okay? Now, the next thing we'll be talking about is an exocyclic double bond, all right? So what do you mean by an exocyclic double bond? Actually, an exocyclic double bond is a type of double bond that is connected to the cyclic structure where one of the double bonds, carbon, the double bonded carbon. Here you have a double bond, all right? Here is a double bond that is connected to a ring. Now look at this double bond. This double bond, is it connected to a ring? No. But when you look at the double bond here, it's connected to ring A. It's also connected to a ring B. Okay, so that means this double bond can enter this ring. It can also enter this ring. So it means that we have 2 exocyclic double bond there. So that means the double bond, there is a double bond that is connected to 2 rings. So that means we have 2 exocyclic double bond. So 2 exocyclic double bond. So which is going to be 2 times 5, which of the double exocyclic is giving us addition of 5 nanometers. So which is going to be 10 nanometers. Okay. So then do you have a double bond extension? Of course, yes. That is, after this diene, this is a parent. So after the diene, there is another double bond that's conjugated to them. So therefore, we have a double bond extension. I think that is very clear. So each double bond extension we add 30 nanometers. Okay. So if you add everything together, then you know that your lambda max is going to give us 315 nanometers. I think that's very clear. Let's look at question number 3 now. Question number 3 says, you have this. So, sorry for the rough sketch. So, now when you look at this compound, you can see that this double bond, they are not in the same ring. So therefore, you can tell us that the parent value is going to be an heteroannular diene. It's an heteroannular diene. So of course, it's going to be 215 nanometers. Now, what are the ring residue? Of course, this diene that are conjugated with each other, 1 and 2, right? So you identify the carbons that bears the diene. So you have this, you have this. So what are the bonds joined to them? The residue joined to them, 1, 2, 3, 4. So we have 4 ring residue, 4 ring residue. And so that's going to be 4 times 5, which is going to be 20 nanometers. Now, do we have an any exocyclic double bond? This one, is it connected to any ring? This one is not connected. It's not connected to any ring. But when you look at this one, it can enter this ring A. Let's say this is A, B, C, and D. Let's say this is ring A, ring B, ring C, ring D. You can see that this double bond here can enter this ring A. It's connected to the bonds. This double bond here is connected to the bond, to the carbon of ring A. But when you look at this double bond, it's not connected to any other ring. Okay. So therefore, we have one exocyclic double bond. So which is 5 nanometers. So when you add everything together, it's going to give you a lambda max of 240 nanometers. I think that is very simple enough for you to grab. All right. Now, question number 4. So you're asked to calculate the lambda mass here. Of course, let's talk about the parent value. We're still on PRED. We're still using the short form of the Woodward-Fieser rule. Okay, so the parent value here, of course, you know that this is an homoannular diene. That is the double bond is in the same ring. So the base value is 253 nanometers. So let's talk about the ring residue. Okay, these are the carbons bearing the diene, and there's no other extension. So Yeah, what are the residues? So this one is connected to this double bond directly. Likewise, this one and also this one. So we're going to be having 3 ring residue. So which is going to be 3 times 5 is going to give us 15 nanometers. Okay, is there an exocyclic? No. Is there a double bond extension? No. So therefore, the lambda max is gonna be 268 nanometers. Okay, so the question number 5. This question number 5 is a little bit tricky. Sure, let me draw it for us. We have this. Now look at this question. Do you know that this structure can be redrawn like this? Let me redraw this structure for you. Now, when you look at these two structures, do you agree that they are the same? Actually, this question be written out like this, be set out for a student like this is actually a trap. So you need to know that this, of course, this can either be here or here because these are the carbons involved. These are the 2 carbons involved. So it's either you put it here or you put it here. So you see the same thing. So because some students may look at it and say this is an heteroannular diene component. No, it's actually an homoannular diene component. All right. So I mean the parent value is going to be an homoannular. Okay. Of course, though you can pick it heteroannular, you are picking this one, but to have the maximum, we pick the homoannular diene component. So the parent value. So the parent value, sorry, there is the a methyl group here. So okay, so the parent value is 253 nanometers because it is homoannular diene. So now let's pick the ring residue, okay? So when you look at this place, so this is, so it's going like this. Okay, so moving from here, so these are the parent diene, moving like this, all right? Then when you look at this double bond, it's also conjugated with this. So we are going to extend it to pick our ring residue. So this one is joined to this double bond. This one is joined to this double bond. This one is joined to this double bond. So that's 1, 2, 3. Then when you look at this one is also joined to this one. When you look at this one, and this one is joined to this double bond, all right? Oh, pardon me, there is still one here. Sorry for not drawing everything completely. So I'm making this one. So, and therefore we're going to be having 7 ring residue. So that's going to be 7 times 5, which is 7 nanometers. Okay. Now, do we have a cyclic? Is this one a cyclic? No. This one can go here, can go here. So it's not the double bond is joined to a carbon that is not belonging to another ring. So it's in between the 2 rings. So when you look at this one too, there's nothing here. It can go out here, it can go out here. So it's not joined to any carbon of another ring. Now, when you look at this one, you can see this double bond is exocyclic to this ring, is also exocyclic to this ring. So we have two exocyclic. So that's going to be 2 times 5, which is 10 nanometers. And do we have a double bond extension? Of course, after this one, we also have an extension here. So double bond extension. So that is 1. And so when we calculate the total now, so the lambda max, therefore, is going to be what? We add everything together. It's going to be. I want to just give you a brief counsel before I solve questions on nodes. Now, the Bible says in the book of Hebrews chapter 9, verse 27 and verse 28 says, "And it's appointed unto men once to die, but after this, the judgment. So Christ was once offered to bear the sins of many, and unto them that look for him shall he appear the second time without sin unto salvation." My dear listener, I just want you to think about your life. You have just one life to live. And Jesus Christ has paid the price for your redemption. Jesus Christ came to the world to die for your sin, so that after this one life of yours, when you die, you can escape judgment. Judgment to be cast into the lake of fire. Because the Bible says that sin is of the devil. Everyone that commits sin is of the devil. Anyone that has not accepted Jesus Christ as their Lord and Savior and have not decided to grow up in the fullness of Christ, to learn about Jesus Christ, they are going to appear on the judgment day because their names are not written in the book of life. Anyone who is not fellowshipping with Christ, who is not growing unto the likeness of Christ, who is not praying to please God, to love Jesus, to walk in the way of Jesus, any of such man will not enter into the kingdom of God. Therefore, what are you waiting for? You have just one life to live. In fact, those people who have not given their life to Christ, they will end in the lake of fire. Hellfire is the end of life without Christ. Hellfire is the end of life without Christ. You don't need to know where hellfire is, but if you die without Jesus, you will not just know the location of hellfire, you will be there. But if you accept Jesus, you will be in heaven. Accept Jesus. Make this one life of yours to count. Make it count for God. Make your life count for God. Hell is the end of life without Christ. The Lord bless you as to give your life to Jesus and wants to grow in him as from today in Jesus' name. You are blessed. The question says that calculate the lambda mass for each of the following compounds. And here are the compounds. So let's do them one after the other. So the question number 1 says cyclo pent 2 in 1 one. So let's draw that. So we're going to draw, of course, this is the parent name that's pent. So we're going to be drawing a pentanone. Okay, so now let's calculate what's the parent value. Of course, this is an enone that's having that is a 5-member ring. So the parent value. So let me remind us of our short form of solving questions for enones. Okay, so the parent value is 202 nanometers. So we'll look at the ring residue. Okay, so of course, this is the enones. So this is alpha and this is beta. As I told you, the ring residue in terms of enones, we're going to be talking about them in terms of alpha is the ring residue on the alpha or the beta carbon. So this is the enones. So these are the carbons involved in the enones. So this is the alpha, this is the alkanone. So this is the alpha, this is the beta, is the gamma, this delta. All right. So on the beta, we have this. So we have the beta ring residue. And so that's going to be what? What's the value for that? That is 12 nanometers. So do we have an isocyclic? Of course, this double bond is an alkenone, so you will not count it as an honorary double bond. So you're not going to make it an isocyclic double bond. So do you have a double bond extension? No. Do you have one direct component? No. So we'll add everything together. It will give us lambda max equals to 214 nanometers. So the question number 2, so let's draw the question number 2. So the question number 2, we have this. So what's going to be the parent value? So of course, this is a 5-member ring, so don't be deceived by this 7-member ring attached to it. So the parent is involving the 5-member rings, and so it's going to be 202 nanometers. And do we have the ring residue? Okay, of course, these are the carbons, the alkanone, then the alkene. All right, so for the alkenones, so of course, these compounds are all alkenones. So you identify the parent functional group. Okay, so these are this. Now, is there any ring residue? Of course, these are the alpha. No. What about the beta? Now we have here and we have here. So we have 2 beta ring residue. And so, of course, that's going to be 2 times 12, and that's going to be 24. So do we have any isocyclic double bond? Because when you look at this one, it's actually, this double bond is touching this ring. So it can enter this ring. So therefore, you will have one isocyclic double bond. So you can simply write isocyclic. So just stress yourself writing the authors. So, and that's going to give us what? 5. So when we sum everything together, we're going to have the lambda mass to be equals to what now? That's 231. So let's solve the question number 3. Now, so what is going to be the parent value for this compound? Of course, you know that this one is a 6-member ring alkenone. So the parent value is 215 nanometers because it's a 6-member ring alkenone. All right. Now, let's talk about the ring residue. Here is the alpha. This is the alpha to this major functional group of higher priority. Okay. So here is alpha. Here is beta. Here is gamma. Here is delta. And this one's greater than delta. All right, so greater than delta. So now, do we have any ring residue at the alpha position? Of course, we have this at the alpha position. So the alpha ring residue, of course, that's going to give an addition of 10 nanometers. Now, do we have as the beta? Of course, this is the beta. We have 1 here. You have 1 here. Of course, to this alpha, I'm sorry. These are the double bonds involved, so the carbon involved. So we have one going to the beta. So therefore, how the beta ring residue. And so that's going to give us 12 nanometers. Now, this is the gamma. Do we have? No. This one, no. Greater here, no. Greater. At this point, we have one here. We have one here. So we have one here. So we have one here. So, and that's greater than delta ring residue. And so that's going to be 18 nanometers. Okay, so now let's talk about the exocyclic. This one, is it exocyclic to this? Of course, yes. So this one, this double bond here is exocyclic to this because it's a double bond bonded to a carbon, a carbon of another ring. So therefore, well, this one, no, this one, no. So we have one exocyclic double bond. So that's going to add 5 nanometers to this. Now, do we have a double bond extension? Yeah, so after this is the enones. So of course this, so after this one, these are the parent. We want to get something. This is an alkanone. So this is the enone, which is what we have here, this and this. So anything after this enone, any double bond that is conjugated to them is an extension. So we have this one conjugated to them. We have second one conjugated to them. So we have 2 double bond extension. So that's going to be 2 times 30, and that's going to be 60 this. So then the next thing we have homoannular diene complex. That's what we have here. So that's what we have here. Here is a ring, an homoannular diene ring that is joined to the major functional group, okay? So therefore we have the homoannular diene component. So that's going to be adding 39. So, and therefore the lambda max for this compound is going to be 359 nanometers. I believe this is very simple to understand. Here is question number 4. Okay, so what's the parent value? Of course, this one is a 6-member ring alkenone. So we are moving here, we are moving here, and we are moving here. So that is the parent functional group. So we're going to be having 215 nanometers. Then here is the alpha. So we have one alpha ring residue. Here is the beta. We have the one beta ring residue. So now we have an isocyclic. So mind you, we are following thread. So we have, yeah. So this ring, this double bond is bonded to a carbon of another ring. So we have one isocyclic double bond. All right. Now, do we have a double bond extension? No, because this is going this way. So we cannot turn back to this, all right? So there's no double bond following this way like this, following in like this. So there's no double bond extension that's conjugated with it. All right, so also this one is not going to be taken as an homoannular diene component because we're following this way is not conjugated with this. This is what I mean. All right, we're following in this way. This is the is not conjugated with it. So therefore, this double bond, because not conjugated with the chain, then it's not going to be taken as a double bond extension, and we don't have an homoannular diene component. All right. So therefore, we have the landmarks calculated as 242 nanometers. All right. So the question number 5. So what is going to be the parent value here? The parent value is going to be 215 because it's 6-membered ring alkenone. Then of course, so this is the alpha, this is the beta, this is the gamma, this is the delta, this is greater than delta. And this one greater than delta. Okay. So at the alpha, there's no ring residue. At beta, we have this one. So we have the beta ring residue. And so it's going to be adding 12 nanometers. Then also at greater than delta, we have this, and we have this, and we have this. Okay, so this, we have this one joined to it here, we have this one joined to this, and this one joined to them. So we're going to be having 3 greater than delta ring residue. So that's 3 times 18. That's going to be 54 nanometers. And also, mind you, these are the enodes. We have the enodes. You have double bond joined to. So this is it. So this is the here. Then this is this one. Then this is this one. All right. So these are the parents. So any other carbon that is conjugated with them is an extension. So you have this one and you have this one. So that's double bond extension. So we have 2 double bond extension. And that's going to be 2 times 30, and that's going to be 60 nanometers. Here, when you look at this one is an homoannular diene component. Okay, sorry, before talk about so what about the cyclic double bond? So when you look at styrene, so you have this one is an cyclic double bond, but this one no, this one no. So we have just one cyclic double bond. So the homoannular diene components, we have one. So you had everything together. So it's going to be the landmarks. All right. So you can see how simple it is. So you should be able to solve any question relating to that. Right. Yeah, so these are the assignments. So you can give your answer in the comment section. You can also reach out to me on this WhatsApp number. If you have need for tutorials, we offer an online tutorial through Zoom. So you can reach out to me on this my WhatsApp number. All right. So if you have not subscribed to this channel, I want you to subscribe. We're still going to be solving questions on IR and NMR spectroscopy. Have a very wonderful day. Thanks for watching to the end of this video. All right. Bye.